It's really great to be here. I'm glad you're all kind of still awake. I do realize this is the 5 o'clock shift, so I understand if you need to doze off for a little bit. I'll try catch you up when you get back. And I'll also be sensitive to the timing, so like if the guys in the front can snore a little bit loudly if I need to wrap things up. Yeah, and it's really great to be here. Thanks to the organizers. It's super exciting to see the growing local community and have so many people visiting us. So welcome. Right, so on to things. I'm going to be talking about reinforcement learning, and there's a split up over 3 sessions. It's today at 5, tomorrow at 5, the next day at 5. So we'll know each other in a weird state by the end of this. And just before I get started, I just want to kind of shout out quickly to all these people for the slides that they've willingly and unwillingly helped me with. But yeah, so the plan for this week is at a very high level. So today I'm just going to talk a little bit about what reinforcement learning is all about. It's becoming a very popular topic, but I'm aware that not everybody has come across it before. So we're going to talk a little bit about the basic terminology, what the idea is, what problems we're trying to solve for. Tomorrow we'll move on to deep reinforcement learning, which is all about reinforcement learning in the age of deep learning, which is really about how you scale your reinforcement learning problems to large and continuous state spaces. And then finally on Thursday, if you're still tolerating me, we'll talk about hierarchical reinforcement learning, which is a different way that you can look at structure in the reinforcement learning problem. And it's really about how you expand the way that you think about actions to look at reusable components, to look at how you can structure the behavior space that you're working with. All right, so hopefully that gives us a decent roadmap to go on for the next couple of days. Okay, so let's start with just basic reinforcement learning, which was always kind of the third area of machine learning, when everyone would talk about your supervised learning, unsupervised learning, and then there's this other thing that people do, which is reinforcement learning, but it's not really machine learning, it's like a robotics thing, and then suddenly in the last couple of years, the machine learning community has kind of owned it. But what's this really about? So reinforcement learning is the branch of machine learning about making decisions. And there's other places where you can look at decision making. There's a whole field of decision theory. But really this is to think about it in a machine learning kind of context. So making decisions, particularly if they're sequential, is about behaviors, right? We want to care about what's going to happen sometime into the future. If I've got to repeatedly make decisions, there's effects to these decisions. And I've got to reason about like the trade-offs of what I'm doing and how this might affect the world as I'm interacting with it. This is really about what behaviors are. And if anyone's got a kind of physics or applied maths background, basically all we're talking about is stochastic optimal control theory if your models are unknown. So if that means anything to you, you can leave now. But that's a connection that I don't actually think is made enough, but we can talk about that a bit later. So I guess everyone's familiar with supervised learning, and you can think of a supervised learning problem as being a single decision point, right? You've got some data, which might be an image, and you've got to make a decision, is this a cat or a dog or whatever the case may be. This is really an extension to when you're looking at multiple decision points. But the key here is that they're sequential. We're not, in general, we're not making the same decision over and over again. We're structuring what we're doing based on what's already happened. So this brings in all sorts of other interesting aspects, like you've got to think about, how do I know if I'm currently doing the right thing? The outcomes of what you do are affected by a whole sequence of things, and we've got to find a way of attributing how did our decisions actually affect this in the long term? Like, where are the links between each decision we've made? All right, so again, I think everyone's familiar with supervised learning and unsupervised learning. So there's different problem settings that this pops up in, and different times when you might want to use these kinds of techniques. So the one that probably everybody's familiar with is playing Go. I'm sure everybody's heard all about AlphaGo, right? So if you're just sitting around and you're terrible at playing Go, this might be the technique for you to solve these kinds of problems. Now again, this, in a similar way to something like chess, is a game where you're making a number of decisions over time. And each one, in and of itself, may not be particularly significant, right? So when you're making decisions, they don't just have to be massive life decisions. They could just be, I have to repeatedly place a stone on a board, and where I choose to put this is going to be a function of where I've put pieces previously and where my opponents put pieces previously. Okay, but that's a very specific setup. So the other place that researchers tend to look at reinforcement learning is in games, right? It's a similar kind of thing, where again you're making repeated decisions. Here, what's different is there's typically more dynamics that's going on in between your moves, or you might have some sort of fixed time budget to make your decisions in. Now, games tend to be one of the most common test beds, particularly at the moment for reinforcement learning. And if you think about this, this is analogous to the way in supervised learning you might have a data set. Right? If we're studying how to make decisions, we can't just, in general, look at a fixed set of data, because we want to know what happens as I do something, right? Every decision I make is going to affect the data that I get next. It's not a fixed static data set. But again, games are quite specific, so a place where this pops up quite naturally again is robotics. And you've got the same sort of setting. You might have a camera or a set of sensors that are giving you data at every point, at every time point, and you've got to make some decisions. These could be, what do I pick up next? Where do I move my head? And importantly here, what happens is the effect of every decision is going to affect this data. So moving your head might change every single pixel you get at the next time point. Whereas if you move your arm, it might only affect some region of your state space. And then there's a number of obvious practical problems. You could think about autonomous cars in this way. You've got to make a series of decisions that get you from point A to B while obeying a number of certain constraints, like the rules of the road, and doing whatever it's doing safely. And then there's less obvious things. So you might think about a treatment plan in healthcare as being a reinforcement learning problem. You've got to repeatedly make decisions about different tests, about changing treatments, and the effects of each of these could run down into the future. All right, so there's quite a broad range of places where these ideas come up, ranging from the test beds we tend to use to problems that are somewhat harder to simulate in a lab, and we can talk about those a bit later as well. So let's jump a little bit into the technical details here. All right, so as I've alluded to, this is an interaction problem, right? So we've got some agent, which is what we call our decision maker, that exists in some environment and is interacting within that environment. And the standard way that this works is that your agent is going to take an action from a set of actions available to it based on the state of the environment. Now, the state is everything we care about. So this could be the set of variables that describe the configuration of a robot arm. It could be the set of pixels from your camera. But that's really what you're going to use to make your decisions. So the agent takes this decision, chooses this action, and then from the environment receives two things. Firstly, the state could change. It doesn't have to, but in general it would, and you receive some sort of reward. And that reward gives you your feedback about how desirable this outcome was. So this is kind of the figure that everybody will have when they talk about reinforcement learning in one way or another, and really talks about this loop of interaction between your agent and environment. Mathematically, in most cases, you'll choose to model your reinforcement learning problem as what's called a Markov decision process, or an MDP. So an MDP is a tuple of typically 5 elements. And the first things we're going to look at here will be the states and actions. So every state, in this case S0 to 2, describes the full configuration of the world. There's cases when you can't see everything. Those are the partially observable Markov decision processes. But let's for now assume that you've got access to every state variable you care about. And then from each of those states, you can choose your actions. The way I've drawn this here is you've got the same actions available in each state, but that doesn't need to be the case either. You've then got T, which is your transition function. And this is something really important. This tells you how the world is going to evolve under those actions that you've taken. Right? So for example, if I'm in state S0 and I choose to take action A0, I might move back to S0 70% of the time and to S2 30% of the time. Right? So this is some sort of dynamic system and which evolves as a result of states and actions. Right? So we're going to talk about this as a function which gives you a probability distribution over your next state given your current state in the action. All right, now this is one of the core entities of your problem. The next one is the reward function, which similarly to the transition function describes something that happens in the environment. But what this does is this gives a single scalar piece of feedback to the agent on certain transitions. Right? So this is going to be a function of a scalar given your state and actions. But what's important to note is this doesn't have to be associated with every single transition. Now this basically tells you what is desirable in this environment. Right? Certain transitions could be positive, certain could be negative. In general, most have no feedback at all. You might think of this loosely as you're trying to learn to play a game of chess, and you might get some positive reward for winning, some negative reward for losing. Most of the time, you get no feedback. And then the last element of our tuple here is the discounting factor gamma. And this talks about how important is it to our agent to receive rewards sooner rather than later. And I'll show you how this comes in a little bit later. So this is called a Markov decision process, and not everyone may be familiar with this idea of what it means to be Markov. So this Markov assumption tells us that actually where we're looking at this transition distribution of what state we end up in, it's not a function of our full history. We don't actually care about the full history. All we're going to do is care about our current state. So we're going to make this assumption in general that the future is independent of the past given the present. So what this means practically is having chosen a certain action in a certain state, I'm always going to have the same distribution of outcomes regardless of how I got to state S2, for example. Okay, so those are the basic ingredients of an MDP, of the bulk of your problem to work with. So let's have a look at a specific example. Now, here's a simple little environment with a little Roomba that can move around, hopefully clean up this dirt in the corner and avoid falling into a hole. So if we think about the ingredients as I've described it, the obvious thing to pay attention to might be what actions this can take. So you can think about this little Roomba in this little room, and if we've discretized the room like this into a 4x3 room, you might say that your actions would be to move one cell to the left or right, or up or down. Okay, and then at point 2, we're just going to say there's an obstacle. Now, your reward encodes what you actually want this to do. So we might say we're going to give it a positive reward of 1 if it finds this dirt, a negative 1 if it falls into the hole, and some tiny negative number for every move it makes. And there's reasons to do this. I'll discuss the rewards in a bit more detail in a bit. And then what we want this to do is move around, try and maximize the total reward that it gathers, and do this through repeated interactions. So we call those episodes, where typically we're going to start the robot up, let it run around for some fixed amount of time or until it dies or something like that, and then learn something, reset, and repeat. And then the bit that I haven't spoken about is the states, which is the different configurations in the world. So you could think about this world as being the states being from 1.1 to 4.3, and you can describe everything you care about in this problem with these states. Right? So if I give you, say, the state of the robot with the picture as it looks here, that describes everything we care about if we know how the thing moves and what the reward function is. Okay, particularly if we know how these actions work. So when I described it as saying you could move up, down, left, or right, I think you all implicitly knew what I was talking about. But actually what I'm saying is there's a transition function that if I try and move north, I might succeed in moving north with a probability 1 and move anywhere else with probability 0. Now that's going to be different if I'm in the top row. It's going to be different if I'm below the below that obstacle. But the nice thing about this kind of domain is it's usually pretty intuitive what the dynamics look like. They needn't be deterministic, as I showed earlier. So you might have something like if I try go north, I succeed 80% of the time, but I could end up somewhere on the side. And if that's the case, then the behavior that you'd really like to see coming out of this looks something like this, right? So if our goal for this agent is to maximize reward, you can intuitively look at this and see that these are kind of roughly the directions the thing should move in to do so. Right? You want it to move, to follow these vectors towards the positive 1 and then not fall into anything. And obviously you could do things like if the dynamics changed, so if instead of moving in the direction I wanted to, I succeeded like 10% of the time and ended up on the sides, then your behavior would obviously change, right? So now you can see here, for example, if I want to move from this cell up, then the best thing to do is move sideways. Right? Hopefully that's clear. So that's if the transition dynamics are different. So depending on what your transition dynamics are and depending on what your reward function looks like, that's going to determine the behaviors that you expect to see for this thing. Now, as it moves around this space, you're going to get different trajectories. And the question might arise of how are we going to evaluate these different trajectories? Because we need to be able to identify that there's good ones and bad ones and find some way of interacting with the good experience that we gain and learning from both the good and bad experience that we gain. So here we look at this entity called the total discounted accumulated reward. So what we're going to do is as this agent moves on a trajectory through the space, we're going to look at the total reward that it accumulates and discount it according to this discounting factor gamma. But that will give us a total amount, a single number that we can look at to evaluate a trajectory. Okay, now the key component to achieving behavior or desirable behavior is to be able to specify what is desirable in each case. And this is where the reward really comes in. Now this is one of the most challenging pieces of specifying a reinforcement learning problem, right? You want to be able to encode all the things that you care about. Because what we're really doing here is we're saying to an agent, there's a bunch of things that can happen to you that I'm going to consider good and a bunch of things that can happen that I'm going to consider bad. And you go and figure out how to act in this environment to maximize the signal. All right, so we tell it what we want, it has to figure out how. So in this case, what we should be specifying is things like winning is good, losing is bad, collisions are usually bad, taking expensive actions is usually bad. And this comes back to this idea, which is obvious from the name of reinforcement learning, that we're learning from some sort of signal that's either kind of a positive thing, like giving a carrot or a stick to our agent. But where this is difficult is that your reward signals typically have these kinds of problems. So firstly, they're sparse. Again, if you're playing a game like chess, you're winning or losing, and it's not always clear along the way what other signals you should give, right? You might give some other positive signal for taking a piece or a negative signal for having a piece of yours taken, but that's actually going to change the behavior, right? So if I gave a positive reward for every single chess piece you take, right, the behavior that's going to get learned from that will be one that tries to optimize your reward, which is going to be encouraged to take extra pieces. But this might not actually be the optimal behavior if you're just trying to win the game. All right, the other factor is that these are usually delayed. Again, in the chess example, if you only get your feedback at the end of the game, like you won, all right, now I might have taken 40 actions to get there. So which were the moves that led me to winning? Did I play well the whole time? Maybe I started off really well. Maybe I got lucky towards the end. Right? So there's this attribution problem that you've got to figure out as well. And then there's this question of the actual values themselves, right? So if I give 1 for winning or 10 for winning, what does that actually mean for my agent? Now, I said this was a difficult problem, and it usually is, and anyone that's been in a corporate environment knows how hard it is to incentivize people. And people don't usually do your literal optimization like these things do. So this is just something that we generally struggle with, is specifying behavior or the desired behaviors that we'd like to see. And I like the story of the rats of Hanoi. So just to give an illustration of how this is a difficult problem. So I think this was in about 1902. There was this rat infestation in Hanoi, in Vietnam. And it was under French colonial rule at the time. They decided, okay, there's too many rats. What we're going to do is outsource the problem, get the population to deal with this. So we're going to just put out a thing that for every rat that gets killed, we'll give you some money. But obviously, the administrators didn't want piles of rat corpses everywhere. So they said, just bring in the tails of the rats, and we'll pay you for each tail that gets brought in. So what happened, I think, is probably pretty obvious to everybody, that you just had people running around cutting tails off rats and going and handing these in to get money. And in fact, it got even worse because people started breeding rats so that they could cut their tails off so they could go and get money. Right? So this gives you an idea that actually setting these rewards is quite hard. Now, you'll see similar kinds of things in a robotics setting, right? So you might say, okay, I want to get my robot to learn how to leave a room, similar to that Roomba setting. So what I'll do is I'll give it a reward of 10 for getting to the door, right? So then it optimizes and ends up taking some indirect route. Okay, that's pretty obvious because we didn't tell it that it has to do this in any efficient way. So maybe what we'll do is we'll give it 10 for getting to the door and then -1 for every step that it takes. Right, so that should get it to the door quicker. And then it optimizes, and then it doesn't move at all because it was 11 steps from the door. So it actually does worse by moving towards the door than standing still. So rewards are difficult to work with, but critical because that describes what we're trying to achieve. Now, given that you can specify these things, what we really care about is this thing called the policy. And this is really the goal of the whole exercise here. I want to come up with a policy, which you could also think of as a behavior, that describes what I should do in each situation, or what my agent should do in each situation. Now, if you think about that, if we go back to the picture from earlier, you had these different states, and in each state we could pick actions. So the thing that was really missing, once you've chosen an action, the way it proceeds from there is under that transition function. So it's choosing the actions that's the important thing to figure out. And so what that tells us is that we have to figure out this distribution, which we usually denote pi, which tells us what action should we take in each state. So can you give us a distribution over actions conditioned on state? And this is in order to maximize our reward from each state, what should I be doing? So you then get the optimal policy, which is really the thing you care about here, because any distribution over your action space for each state is a policy, and your optimal policy is just the one that's going to give you the maximal total rewards. Okay, and this is really the thing we want to learn. Now, you can't just look at the immediate rewards, right? So if I've got two options in front of me, and one gives me a reward of 5 and one gives me a reward of 1, right? It's not necessarily the case that I should take the action that leads to the 5, right? Because as I've said before, there's this notion of delayed rewards, which means you might get some good rewards later on, and not in the immediate setting. So it might be a small trajectory to get some small positive feedback, but that might end your interaction, whereas you could have taken a slightly longer path and get proportionally a much higher payoff, right? So what the little toy example here indicates is that you can't act myopically in each case, right? You've got to think about these trade-offs of what rewards am I getting when, and how do I think about the future to maximize what I'm getting. Right, now this is actually the thing that makes one of the things that makes RL a complicated problem, because you can't just run your greedy optimization from every state to say, pick the immediately most beneficial action at every point. So you could think of, if our reward isn't giving us that information, that's really rolling in all the long-term benefits, we can think we might want some other proxy of this information. And this usually comes in as what we call the value of a state or the value of an action. Right now, where the reward was just your problem encoding that just said, like, I want to win the game, I want to do this efficiently, or whatever the case may be. If you can kind of conflate all the factors that may happen from any point into a single number, that would be really useful, because then we could act greedily with respect to that. And the way I'm going to introduce that we talk about this is called a value function. So your value function is this function v that tells you what is the total reward I can be expected to accumulate if I start in a state S and then follow some policy pi. Okay, now if you think about that, what that's actually going to tell you is that's going to roll together all these ideas of all the rewards I might get over the course of some trajectory, and that trajectory is going to be determined by firstly taking actions according to pi, and then transitioning according to the transition function. Right? So at each point in time, whatever state I'm in, I'm going to pick an action. The state's going to evolve under the transition function. I'm going to receive some reward. I'm going to take another action, again according to the policy pi, transition to another state, receive some reward, and continue with this. So if I start in state S and follow policy pi, I can be expected at the end of some trajectory to get a certain amount of reward. Okay, and this looks like this, right? So we're looking at the instantaneous rewards at each point, following this policy, and then discounting according to gamma by how far it is into the future. If you're running episodically, your gamma might often be 1, so you don't worry about that. But this lets you also deal with continuous tasks that don't terminate. So this gives us a way to ask the question of how good is a particular state under a particular policy. Now it should also be clear that if you change your policy, the value is going to change. All right? If I'm in a particular state, whether this is a good or bad place to be depends on what I'm going to do next. So, an example. Let's say you've got this little 5x5 grid world with 2 teleporters in it. One's going to move you from A to A prime and give a reward of 10, and the other from B to B prime and give you a reward of 5. And if every move you make might also give you a reward of -1. So if you can just move around in this domain, if you look at what the value of each state may be, you'd get something that looks like this. So these views are equivalent. The one is just the numbers, and the other is just a visual depiction that's easier to see. But what you can see is if you treat the brighter states as higher value, then obviously the ones nearer to these teleport points are going to be better, right? Because those are the maximal reward actions or transitions you can take. Would be anything that ends up on this A or B state, and then things diffuse from there. Right? So the better states are the ones that are closer to those points, because under a random walk, you're most likely to end up there. On the other hand, if you had an optimal policy, so you were acting optimally, which would be, say, according to this policy over here, you'd get a much clearer distinction of the value propagating from the same points, right? So now if you have a look at the values in these states, it should be quite clear that there's a strong connection between these values and the policy, right? So if the way we could think about the reward function is just there's 2 transitions that have positive reward, everything else is negative in that we had -1 for every transition. But actually these numbers here encode a notion of goodness of each state if you're acting optimally, right? And that's kind of what you'd expect. Like the further away you get from these desirable locations, the lower the value of those states would be. And that kind of gives you this gradient to follow up to those points. Is everyone on board so far? Yes. Yeah, so in some formulations, you'll have like an extra element in the MDP tuple of the initial state. Most people tend to not include that, and then like as you're running the algorithms, you choose your initial state randomly. Anything else? Yeah. You mean the total number of states? Yeah, so typically with these problems, yeah, the total number of states will be fixed. And you can think of like the whole state space potentially as being like every pixel in your camera, for example, right? So the value of each state could be different, but there's a total number of possible states that you could be expected to see. So yeah, and typically you don't change those as well. Yeah. Anything else? All right. So if you ever look at this example value function that I've drawn up here, what should be clear is there's kind of a recursion going on, right? So the value of a state depends on the value of its neighboring states, right? How good it is to be here depends on how good it is to be at the places nearby there. So value functions are inherently defined recursively, right? So your expected return of being at a certain state and following a policy depends on the value of being at adjacent states, right? This is only a good state because one step further on from there is taking me closer to my goal. So this is really nicely formulated by the Bellman equation, which gives us recursive property that the value of a state, S is some function of the value of other states S prime, and that is going to depend on two things. The first, there's the immediate reward. So if I'm in this state and I take an action according to this policy, that gives me some immediate reward. And then that will transition me into a subsequent state, and with some probability it could transition me into any subsequent state, as defined by this transition function t. And so if I kind of look at the sum of all possible states I could end up in, and weight the values of those states by the probability of getting there, that's going to give the full value of an individual state. Okay, so the goodness of this state under a certain policy is like the weighted average of the goodness of all the other states I could end up in under that policy, plus the amount of immediate reward I get by doing that transition. So then you've got this recursion that looks across all your states. And we're going to use this to give us the first solution to the reinforcement learning problem. But first, in a similar way, you can look at the optimal Bellman equation, the Bellman optimality equation, which is the same functional form, and I'm using here this little asterisk to denote optimality. But we're going to look at the max operator. So what this is if you're acting under the optimal policy, the value of a state doesn't depend on this distribution over all other states. It depends on the best one that you could move to. Right? So this should hark back to this idea from that example I gave where you had this kind of neat gradient. So you could intuitively think of moving to the best state from each particular point as being the optimal thing to do in that state. Now that I've defined this value function v, I'm also just going to quickly define a similar one for actions. So where v was a function of just the state, we can also look at what's called an action value function, which is the value of a particular action in a state if I'm thereafter following a policy, right? So how good is it to be in state S, then take action A, and thereafter follow a policy pi? And again, that policy is important because there's a difference between taking a particular action if I'm thereafter going to act optimally or if I'm thereafter going to act randomly. So how good is this particular action? And it's the same kind of thing, right? So we've got this recursion here that we can look at the adjacent states, or you can define it in terms of the action value functions for adjacent states. But it's the same basic idea, right? So I've got a reward and I've got a transition. Now, as I've been talking about, there's this really nice connection between your value functions and your policies. Okay, so if you take your value function for your optimal policy right? So your optimal value function. That directly from there, you can read off a policy, or you can read off your optimal policy. So optimal value functions and optimal policies are in a sense interchangeable, because if we go back to this example over here, if that's the optimal value function, and I move in the direction of greatest ascent of value, that's going to give me the optimal policy. Okay, so if I'm in a state and I just move deterministically in this direction, where there's the greatest increase in value, I'm now acting optimally. And then obviously what that means is that finding your optimal value function and finding your policies are equivalent. Your optimal policies are equivalent, because you can just act greedily. Yes? So if there's two transitions that have equal value, then you can take any linear combination of those actions, and that'll be optimal as well. Yeah. Yeah. All right, so these two that go in all four directions, that's just because when you transition into those states, you teleport. So you're never actually taking a decision in that point. Yeah, it's just an awkward depiction of what happens there. So if I'm in, say, the corner state here, and I move into this one, I'm going to teleport down there according to this jump. And so I've never actually made a decision on that state. Yeah, yeah. Cool. Anything else? All right. So this really describes, so at this point, we've now spoken about what makes these problems, these MDPs, and like starting to get at some solution concepts here, being these value functions, V and Q, as well as the policies. So we can use the Bellman equation to start giving us solutions here. So if you have a look at this, right, you could write out one equation for every state in your state space. You could do the same with the action value functions. You can write these out as a system of value function equations and solve these, right? But obviously you can't just do that trivially, because you've got this max operator, right? So we can't just write this out, invert matrices and solve. So the obvious thing to do here is to be iterative in our solutions. Right, so again, think of this as you could write one of these equations for every single state, and then we now solve the whole collection somehow. And what we're trying to do is to learn how good each state of the world is if we're taking all of these into account simultaneously and being able to look perfectly into the future. So the simplest, most straightforward thing to do in this case would be dynamic programming, which in the RL case is called value iteration. So what you can do here is follow this very simple procedure. Right? We can iteratively update V. If at each iteration for every state, we're just going to update according to the Bellman equation. Right? So we're going to take from some initialization, we're just going to repeatedly update run through every single state and update based on what its neighbors' value functions look like. Okay, so we can just compute this. So if we've got the transition function, and we've got the reward function, and we've got a current estimate for the value function, you can just repeatedly take the max over these things and keep updating these values. Right, and that's going to give you a way of computing a value for every state in the domain. Okay, that should be super simple and trivial. But the reason this isn't a thing that's like very satisfying is because you need the full MDP to be able to do this. Right? So I can only compute this iteratively if my transition functions and reward functions are known. Now, if you knew everything, then your domain tends to not be very interesting, right? But what this tells you is you can think of the transition dynamics as like a model of physics, and your reward functions like your objective function. So if you know all of this, you know everything about your problem, all you have to do is kind of effectively backwards propagate your solution. So it's similar in that sense. You've got other kinds of dynamic programming that come up looking like algorithms like A star. If you know everything about your domain, you can just compute things. But in general, because we don't have this, we've got to do something else. Now, this is where the connection that I mentioned earlier to optimal control theory comes in, right? So this problem, as it's specified here, is like a discrete state optimal control problem, where we just need to compute for every state this goodness value, and that gives us our trajectory. So if these things are unknown, we've then got to do something else. And most RL algorithms you'd come across would work in this way, right? You've got to generate some samples from your environment and use that to learn. And so as a simple example, right, you might have your little agent and you can take some random actions in your domain, and these you could think of as samples, right? So by collecting enough samples, we can learn enough about the domain that we can then try and optimize the behaviors, which is what we really care about. So we could just take a set of these samples everywhere, and some of them are good, some are bad, sometimes things change, sometimes they don't. Right? And you could think of the experience you're going to gain here as coming from this tuple, or being of the form of this tuple, which is I was in a state, I took an action, I received some reward, and I transitioned to another state. So every time you take an action in your domain, while you're learning, you're gathering data of this sort. So this is where reinforcement learning really ties into this concept of learning from experience. It's not like we've got these a priori data sets where you just look at everything and try and extract something from it. But here you really have to interact with your environment. Right? You've got to collect these tuples that tell you something about your domain. Now to do this, there's two things you need. Firstly, if I'm moving around my environment collecting this information, I clearly don't have an optimal policy yet, so I need some mechanism for choosing what actions to take. And then I need some model or some mechanism of keeping track of what I'm learning. So as far as choosing the actions go, there's this nice notion of a bandit problem. So this is a little digression. These kind of slot machines in casinos, these one-arm bandits. If you think of the version where there's multiple of these, right? The multi-arm bandit problem. You walk into this casino and you've got to choose what is the best arm to pull in each case. Now, if you pull one of these randomly and it gives you some sort of payout, what do you do the next time, right? So this gives you 5 rand or dollars or wherever you're from. So you've pulled one of these arms. This has given you some payout. You haven't pulled the other ones yet. What do you do? Now, there's this trade-off that we talk about in reinforcement learning called exploration versus exploitation. So exploration means let's try something else. Exploitation means let's go for the best thing we've done before. Right? And there's actually a lot we can talk about here, but just to get the basic notion across, this is a key thing that you need to bear in mind, right? So as I'm moving around, I've got this little agent moving around this domain. I've got to draw samples that are either new things to tell me something else about the domain, or something I've seen before, because firstly, that might be helping me with what I'm trying to achieve, but secondly, it's giving me better estimates of what's happening in this domain. Right, so we'll look at this in a very simple context here, but as I said, what you want to do is trade off this gathering of new information and exploiting the information that you've already got. So this exploiting is usually acting greedily, and exploring is usually acting random. And this is really this tension when you're acting not under an optimal policy of what you should be doing. So there's a couple simple exploration strategies. There's some reasonably sophisticated things you can do here, but most commonly there's two strategies people follow. So one is what's called epsilon greedy, which says with some probability we're going to exploit. We're going to take the best thing that we've seen so far. And with some remaining probability, we're going to just act at random. Now, if you do this, and with the right value of epsilon, you're going to trade off between the two in a way that ultimately ends up giving you all the information you need to be able to converge as you're learning. The other strategy that people often look at is like a softmax strategy. So if you've got some action value for each action in that state, you can sample according to a distribution under those values. So you're not just choosing the maximum, but you've got some like soft distribution over all possible values. All right. So this gives us a way of acting when we don't yet have an optimal policy. right? So if I can act epsilon greedily, as I'm learning a policy, I can start off by acting randomly and over time start exploiting more and more. Then as I'm learning, I need to keep track of what I'm learning. For this, we're going to use value functions, which we've spent some time on already. Now, probably the most canonical way of learning in these settings is what's called TD learning, or temporal difference learning. And the idea here is that as I'm learning, I'm going to update some value of some estimate of my value function. So I'm going to go around and collect samples from my domain of these transitions, states, rewards, and states. And I'm going to use that in this way to update my value function. So what we're going to do is, at each point, as we collect this data, we're going to form a new estimate of our value function by looking at this, by looking at what's called this TD error. So this TD error consists of saying, what is the reward, what is the immediate reward I'm going to be receiving, as well as what is my estimated future reward from that state, right? Because if you look at this, you've got your VI at S prime. S prime is your successor state. You're saying, what is the value under my current model of how good that state is? So this is what's called the TD target, and the TD error is the difference between that and the current estimate of the value function for this state. All right, so you've just received some reward, and you're going to use that to update your estimate here. So you can think of this as saying my new estimate of the value of this state is my old estimate plus some step size times this error. Okay, the step size, alpha, is called the learning rate, and this is, okay, there's often quite a lot of hyperparameters in here. I'm not really going to dwell on those, but this gives you the way that you adapt your value for each particular state as you receive a new sample there. So if you look at this kind of as a pseudocode algorithmically, what we're going to do is we're going to start our agent in our domain and run over multiple episodes, where each episode is the agent starts randomly, moves around for a while, learns something, and then typically we'll reset it. And during each episode, we're going to repeatedly draw an action, take that action, and update our value function. Right? So these three lines here are really the core of this learning algorithm. And actually, most reinforcement learning algorithms have this core flavor at their center. We're going to keep taking actions, where, as I said before, you could use something like your epsilon greedy learning. You take that action, you observe a tuple, and you learn. Right? Now, notice the important thing here is that you're learning as your agent's interacting. Right? So you can think about this as if there's some sort of bias to the policies that it's learning from, or the way that it's sampling actions, it's going to get a biased view of the world. Like if it doesn't end up in some parts of your state space, it's never going to learn about them. Okay, any questions at this point? Cool. Okay. So this gives us a very straightforward way to learn your value function with successive estimates as you're exploring in your world, as you're experiencing different states in your world, right? Now, as I mentioned earlier, that then, if you had the optimal value function, and the methods here do converge, they do converge, not a question, you can directly read off from that your optimal policy. But then the way I described it here, we weren't using our action information, we're just using the state information. So you can do the exact same thing, right? So instead, you could learn with your Q functions rather than your value function, your state value function. And there's technical reasons to do this, and the one is that you've got to do a one-step look ahead if you're just using the state value function, right? So if you think back to that example I had, if I'm looking at the states that I should move to next, I've actually got a query for each action, what state that would end up in, right? So in that case, it was pretty obvious, because you just look north, south, east, west. But in general, like you might have an arbitrarily complex domain, and you might have to actually simulate each action, see what state it ends up in, look at the value of that state, and then take the maximum of those. So to get away from doing that kind of of look ahead, there's other models that you can use to look at that would learn the Q value function instead. So the simplest and most common of these is called Salsa, and that's because it's learning from Salsa, which is state, action, reward, and then the next state and the next action. And this is going to follow the exact same pattern, right? So we initialize our value function at the beginning of learning, and then we're going to learn over a number of different episodes, and again, where each episode starts, the agent runs for some period of time, and then it terminates. Either it receives like a total number of positive or negative rewards that are capped, or we'll just terminate it after some duration. So for each, we're going to initialize, we're going to choose an action from the state, and then for each episode of for each step of the episode, you're going to choose an action, and that's your acting. We're then going to choose a next action. I'll show where this comes in. It's a form of look ahead, but here we're using this to learn for the Q value functions. And we're going to do the exact same update, right? So you've got the same structure of the TD update, that you've got your target minus your current estimate, except we're just looking at the function Q in this case rather than V. And that's where we do our learning. And then we just transition to the next state, having chosen the next action. Okay, so what's happening here is we're just repeatedly choosing an action from a state. We're using this policy that's coming from Q. I'm just talking about that generally because that could be doing something like epsilon greedy. So we're picking our next action. We're going to observe in the next tuple, the next Salsa tuple. Use that to update your Q functions and repeat. Okay, so it's the exact same structure of algorithm. Any questions there? Cool. Okay, cool. All right, so now choosing these actions, right? So that choosing the next action thing was a little bit awkward. So I needed to know, if you look at the way we update this policy here, we're updating based on this next action that we're choosing under this value function. Okay, so I've already kind of pre-sampled the next thing I'm going to do, and what that's really telling me is that's telling me that I'm learning according to the policy that's determining my next action. All right, there's a subtle complexity if you're not doing that, which comes in because the policy that you're learning is actually changing. Right, so every time I update this Q value function, it's actually a different policy that I'm acting under. Right, every time I receive a new tuple and I update this value function, because you can translate directly from value functions to policies, that's changing. Right, so I'm kind of learning I'm learning this value function under a changing policy, which in general has different dynamics, right? So I need to be able to specify here the policy, like with the one-step look ahead while I'm learning, so that I update based on what's going to happen next, right? Because if you remember, the definition of the value function was under a particular policy, right? So that policy couldn't necessarily change while I'm learning, right? And this is what's called on-policy learning, all right? So all the learning I'm doing is under a fixed stationary policy. But that doesn't need to be the case in general. We could do what's called off-policy learning. Now, off-policy learning, there's a whole lot of things that come in here, but basically this gives you a way to learn using other policies, right? So you don't have to have the same exploration policy while you're learning. And what's neat about that is you can also use like other behaviors. So if you've got samples from other agents in your domain, maybe you're watching agents move around in the domain or experts or something like that, you can gather their experience as well and use that to learn as well, right? And then this gives you the off-policy version of this, which unsurprisingly is very similar again. This is called Q-learning. So we're going to follow the same procedure again, which initialize our value function, and then for every episode we're going to repeat, initialize, and then do the following thing. We're going to first choose an action from the state under our policy. We're going to take that action, and then update. Now the update here is going to be a little bit different because instead of looking at the next state we move to, we're going to take the best action under our current queue function. Okay? So before we were looking at A prime as being the next action that was going to be generated by the same policy. But here we're being cognizant of the fact that actually this policy is changing. So we're going to learn against the best thing that we could have done from anything we've seen before. Right? So actually some of these samples now could have come from other agents, as I said. Right? Because we're going to learn against the best thing. So we're taking this queue as being a proxy for the queue star. And we're deriving kind of that optimal policy from it, even though we know at this point it's not optimal. And we're going to repeat that until it's terminal. Right, so it's a simple modification, but what that means is we also don't now have to do this kind of look ahead at all. So we've gone from using the state value functions, which had to do look aheads, and that was with TD learning, to Salsa, where we had to do some small look ahead in order to be using the same policy, to now maximizing over anything we've seen before, which has no look ahead at all. All right, I'm going to give you a simple demo of how this learning works. So in the domain based on the one I showed earlier. So what you're going to see here is in each of these cells, there's 4 little triangles representing the value of each action. Now, as this is learning, it's starting off taking actions completely at random. Now, you could see at the beginning everything was black, so all these values were initialized to 0. It didn't know anything about the domain. So it's taking actions at random, and as it does that, it's gaining more information. So it's updating these values as it gets that information. All right, so after 100 episodes here, this is what it's seen of the world. It hasn't taken everything, but you can see that these are starting to kind of bleed out. So this -1, if it's taken it a few times from here, it's learned that that's a negative. Going up from this state is negative. It's learned that going right from this state is negative, but it hasn't taken these things that many times, right? So as it's gaining this experience, as opposed to doing like a direct method, such as value iteration, it can't just compute the optimal value for each action or each state directly. It's got to do this through repeated interaction. Is the example cool? All right. Yeah. Yeah. So was the exploration in the beginning of this? Well, they had to be at the beginning, right? Because you need some way of choosing actions. And as I said earlier, the most standard thing to do with an algorithm like Q-learning is you typically start of exploring like 100% of the time, because it doesn't make sense not to. You don't know anything about the domain yet. And as you spend more time there, you want to decay the amount, your probability of exploring. So if I've been acting in the same environment for ages, I can pretty safely just act according to what I've learned there. Maybe once in a while take a random action. So typically what's done is you start with that value somewhere between 0.9 and 1 and then decay it as you're learning. Anything else? So what you're going to see in general as you're learning will be a curve that looks like this. And depending on the complexity of the problem, this will jump at different times. But generally, you start off, and we tend to plot the performance of these as your total reward per episode as a function of the episode. And what you'll see is in your first few episodes, you tend to do quite badly. In particularly difficult problems, this might be flat at a low value for quite a long time until it discovers like the positive states. So you could easily imagine in this previous case that for the first number of episodes, it didn't even encounter that positive state. Let's say we timed out after 10 actions, for example, each episode. It might be a number of episodes before it discovers any positive reward for the first time. And so you might see a number of episodes at the beginning where nothing good is happening. And then gradually this is going to improve, and the shape of your learning curve will depend on things like how you're decaying your exploration parameters and so on. But typically what you're going to see is that you start with some terrible reward, and after some number of episodes, you end up plateauing like at whatever passes for optimal behavior in the domain. So these are kind of the graphs that you'll typically see in an RL paper. All right, so that's kind of what I wanted to talk about today. So we've just run through setting up an RL problem as the problem of learning behaviors in an MDP. A really important thing to think about is the rewards. And then your solution concept that you really care about is the optimal policy. But for the methods that I've spoken about today, these very simple methods, you need value functions to get at these. And an important aspect to think about is your trade-off between exploration and exploitation. Now, when the models are like fully known, so that's a transition model and the reward function, then you can use something simple like value iteration, which is a dynamic programming-based approach. But when you don't have that, you've actually got to learn from experience, which is really what people recognize as the core of reinforcement learning. And there's a whole zoo of different models and different algorithms, such as temporal difference learning, Salsa, Q-learning. So tomorrow I'll talk about how to take these models and move them into the deep learning era with really working with larger state spaces. And then, as I said again on Thursday, we'll talk about what to do in richer action spaces.